Our next subject is analysis of variance, or often referred to as Anova testing. And this is back to numerical data again, but when we're dealing with more than two populations or more than two sets of data. So the article, could mean platelet volume be a predictive marker for acute myocardial infarction? Myocardial infarction is the heart attack. Described an experiment in which 4 groups of patients seeking treatment for chest pain were compared with respect of mean platelet volume. The purpose of the study was to determine if the mean MPV was different for the 4 groups. In particular, for the heart attack group, if so, then MPV could be used as an indicator of heart attack risk. So researchers need to compare the means from the 4 treatments of the groups to determine if the 4 means were equal, or if at least one of the means was different from the rest. So in order to compare the means, the researchers must use a procedure called a single factor analysis of variance, or Anova. Single factor means we're only looking at one variable, changing one variable. When 2 or more populations or treatments are being compared, the characteristics that distinguishes the populations or treatments from one another is called the factor. In this experiment, the factor is the clinical diagnosis. The 4 groups were non-cardiac chest pain, stable angina pectoris, unstable angina pectoris, and myocardial infarction. In other words, a heart attack. So whether the null hypothesis of equal means should be rejected depends on how substantially the samples from the different populations or treatments differ from one another. Consider the following example. So here we have 3 different means from 3 different populations, and you notice the means of the samples are different. In group A, notice that the 3 samples seem to have very different means and very little variability in each sample. So you can see that's all sample A, that's all sample B, that's all sample C. Very little variability, so very little overlap in the samples. So here it would be very doubtful that the 3 means would be equal. In group B, however, we notice the 3 samples have very different means again. However, there's a large amount of variability in each of the samples. So it would be plausible to believe that they could be overlapping. Because sample 1 is these orange dots, or actually sample 1 should be the green dots, the aqua. Sample 2 is the orange, and sample 3 is the blue. So even though the means are the same distance apart, because the samples themselves have a lot more variability, it makes it plausible to think that the means might actually be the same of the whole populations. So the phrase analysis of variance comes from the idea of analyzing the variability in the data to see how much can be attributed to differences in the means and how much is actually due to variability in the individual populations. So notation in the Anova method, K is the number of populations or the number of different treatments being compared. Capital N, well, little n1 is the number of items in the first treatment or the first population. Little n2 is the number of items in the second population, and so on. So capital N is just all the little n's added together. In other words, it is the total amount of items in the whole experiment being done. T is the total. Now, T could actually be found by adding up all of the little data points, or a shortcut is just to take the size of each sample times its mean. Assuming that the mean, the x bar 1, x bar 2, and so on, assuming that none of those are rounded off due to uneven answers. But capital T is just the total of all of the individual values. So then x bar bar is often referred to as the grand mean. It's the mean of all the values. So x1 bar, that's just the mean of the values from set 1, and x2 bar is the mean of the values from set 2. X bar bar is the grand mean. That's the mean of all of the values, all of the sets put together. So the total number of observations is capital N, T is the grand total, and X bar bar is the grand mean. More notation. So a measure of differences among the samples. Sample means is the treatment sum of squares, denoted by the SSTR, the sum of the squares treatment. And given by SSTR is the size of sample 1 times the difference between its mean and the grand mean squared. Size of sample 2 times the difference between its mean and the grand mean squared, and all the way up. So it is the differences among the sample means and the grand mean. A measure of, so it's often called the measure of variability between treatments. A measure of variability within each sample is often, again, called the within treatments, called the error sum of squares, or the sum of the square errors, is degrees of freedom, not just sample size we go off here. So it's n1 minus 1 times the standard deviation of sample 1 squared, n2 minus 1 times the standard deviation of sample 2 squared, on up. Each sum of squares is associated with a number of degrees of freedom. The between treatments is k minus 1, so the number of different treatments minus 1, and the within is capital N, the grand total number of observations minus the number of sets. So the degrees of freedom comes from adding together, where capital N is from adding together all of the sets. Well, the degrees of freedom for the within treatments is the degrees of freedom for each of the individual sets. So it's each set minus 1. So it's capital N minus 1 for each set would be just minus k. So the mean square is the sum of the squares divided by its degrees of freedom. So SSTR divided by k minus 1 and SSE divided by n minus k. So the single factor ANOVA test. Our null hypothesis is that the means are all equal. The alternative is at least one of the means is different. Our test statistic, F, is MSTR, the mean sum of the squares between the treatments, and MSE, the mean sum of the errors. Now, K minus 1, that's the degrees of freedom that goes with the MSTR. N minus K is the degrees of freedom that goes with the MSE. There's a reason I point that out, and we'll look at that in just a minute. When HO is true, the mean MSTR equals the mean MSE. So if it's true, HO is true, that should be equal to 1, or F statistic should be 1. When HO is false, the mean of the mean square of the treatments is greater than the mean for the mean square errors. So our p-value is the area under the curve, the appropriate F curve, to the right of the calculated F value. In other words, greater than the calculated F value. Our assumptions for an ANOVA test. Each of the K populations is approximately normal. If sample sizes are large, in other words, 30 or more, we don't have to worry about this. Very seldom in an ANOVA test do we take samples quite that large. Individual plots can be used for each of the samples to show normality, or dot plots, or even individual histograms if we want to, just to show that approximate normality. Sample sizes are small, then a combined normal probability plot should be used to check the normality. This is that norm quantile plot to see if the points lie on that straight line. First, find the deviations from the respective mean in each sample, then combine the deviations to create the normal probability plot. The K normal distributions have identical standard deviations, so we're assuming the standard deviations between the populations are approximately normal. Well, there's a formal procedure to check for equal standard deviations. There's actually a hypothesis test for checking that. Its use is not recommended due to it's very sensitive. Even if it's slightly different, the Anova test won't work. So the observations in the sample from any particular one of the K populations or treatments are independent of the other. So the populations are independent. No overlapping values between them. And selecting values from one population does not affect the chances of getting values from another. When comparing population means, the K random samples are selected independently of each other. When comparing treatment means, treatments are assigned at random to subjects or objects. So that was just random selection. So here's our information. Now here we actually do have fairly large samples for our cardiac patients. We have the mean and the standard deviation for each of those samples. So we're going to state our hypothesis that the four means are equal, and of course the alternative is that at least two of the means are different. We're going to verify our assumptions. The box plots there show that they are approximately normal. To verify the equality of the standard deviations, those are relatively close. Remember what we do is as long as none of them are more than twice any of the others, we assume that they're approximately normal. So here the 1.07 is the largest, 0.69 is the smallest, and 1.07 is not more than twice of the 0.69. The subjects were randomly selected and the groups for the individuals are independent. So let's calculate the sum of the square terms, the sum of the squares between treatments and within treatments. So the SSTR is going to be 35 times sample mean minus the grand mean. Well, the first thing I'm going to do is find the grand mean. The grand mean, the 11.315, that was found by doing 35 times 10.89. So the sample size times the mean for each of them, plus 35 times 11.25, plus 35 times 11.37, plus 35 times 11.75. We added all those up, then we divided by the total, which is going to be 140. That's 35 plus 35 plus 35 plus 35. So that gave us that grand mean of 11.315. So then SSTR, that is the size of the sample times the sample mean minus the grand mean and then squared. Size of this sample times the difference between the sample mean and grand mean squared. And on down the line, get us a sum of the squares between treatments of 13.199. Our sum of our square errors within the treatments then is n minus 1, so that's 34, times the standard deviation squared, so 0.69 squared, on down our line, giving us 101.88. Now, degrees of freedom for the SSTR, there are 4 sets here. So 4 minus 1, there's 3 degrees of freedom. So the 13.199 divided by 4 is 4.4. For the mean sum of the square errors, or square error, I should say, take the 101 times, we have 140 here total minus 4 sets. That's where we get the 136. That comes out to 0.749. So our test statistic, the F test statistic, is found by dividing those two to give us 5.87. So with 3 degrees of freedom in the numerator and 136 degrees of freedom in the denominator, remember that 3 was from up there, the 136 down here. In our F chart, we have to look at that 3 degrees of freedom. Usually it'll say either in the numerator or in the between treatments. and the 136 would be either the denominator or the within treatments. We look that up and we find the p-value of 5.87 is less than 0.001. So with alpha of 0.05, we will reject the null hypothesis. There's at least one of those means is different from the others. So to summarize it, we often use a tool called an Anova table. It helps us organize this a little bit. And to do that, we need one other sum of the squares term. That's the sum of the squares total. That's each individual value minus the grand mean squared. Now, we don't actually have to calculate this because the sum of the squares total is equal to the sum of the squares between plus the sum of the squares within. So there you can see that relationship has to hold. So this is a fundamental identity for single factor ANOVA, which saves us a lot of calculation. So here is our ANOVA table. A lot of times this degrees of freedom column is moved over one because it's this number divided by the degrees of freedom that gives us this number here. But either way, they can be set up either way. So here is our between treatments, the SSTR divided by the degrees of freedom, giving us that mean square. Same for the error for the within treatments. We find those values in that line. This here is just a double check the totals. And then our F statistic is found by dividing those two. When the analysis is done, we can fill in the p-value either using software or from the table. So there's our set. The p-value here is close to 0, so we just put in 0 there. Now we know that at least 2 of the means are different, but which 2? So we're going to go through an analysis of this and see which ones are the ones that we assume are different. To answer the question in this study, we need to know if the mean MPV for the heart attack group is the mean that is different. So what do we do now that we know that at least 2 of the population or treatment means are different? How can we tell which of the means are the ones that are different? We need to use a multiple comparison procedure, which is a method of identifying differences between means. The Trudy-Kramer, the TK multiple comparison procedure. This procedure is based on calculating confidence intervals for the difference between each possible pair of means. If the interval contains the value 0, then there is no significant difference between the means involved. If, however, the interval does not contain a value 0, then the 2 means are significantly different. When there are k populations or treatments being compared, the number of confidence intervals necessary is given by k times k minus 1 over 2. So here we've got 4 treatments. 4 times 3 would be 12 over 2. There's going to be 6 different confidence intervals. And that confidence interval, very similar to our confidence intervals, our regular confidence intervals for two population means, only instead of having like a z or a t value there, it's a q value. It's a standardized value that we're going to use. It's called the studentized range critical value. We use the MSE inside with the sample sizes. So the TK intervals are based on a probability distribution called the studentized range distribution. So the 2 means are judged to differ significantly if the interval does not contain 0. So if the sample sizes are the same, we can just use that plus or minus q times the square root of the MSE, the mean square error over n. So since they are the same here, we can do that. So we're going to need 6 confidence intervals. For mean 1 minus mean 2, these two, we calculate the difference, and then the 3.68, that's our Q value. We'll see how we get that later on. Sample sizes are the same in each treatment, so we can just use the MSE with the 0.74, remember that came from our Anova table, divided by 35, which is the size of the samples. This is the critical value for a 95% confidence interval when k equals 4 and degrees of freedom equals 120. That's the closest we have to 136 in our k table. This interval contains 0. It starts out negative and goes positive, so it contains 0, so there's no significant difference between those two population means. So we do this for all of them, and we find this is the only one here where we have an interval that does not contain 0. So mean 1 and mean 4 are the two that significantly differ from each other, which would make sense because those are the ones that are the furthest apart, mean 1 and mean 4. Realistically, if I'm doing this, I do those two first, and if there's no significant difference there, I don't need to do the rest. So there he is. The only interval that does not contain 0 is the mean MPV between the patients with non-cardiac chest pain and the patients with heart attacks. So, summary of the TK procedure. List the sample means in increasing order. Identify the population mean just above each, or identifying the population above each of those sample means. Just like that. Using the TK intervals to determine the group of means that do not differ significantly from the first in the list. Draw a horizontal line from the smallest mean to the last mean in the group identified. So if the sample means for populations 3, 2, and 1 are not significantly different, we don't have to worry about them. We'll just draw a line under them. So we know that those are safe. If the sample means for population 2 is not significantly different from 1 and 4, so 2, 1, and 4, those are adequate. Continue considering the means in the order listed, adding new lines as needed. So here's our heart attack data again. We'll summarize these TK intervals. 1, 2, and 3. 1, 2, and 3 are not significantly different from each other. 2, 3, and 4 are not significantly different from each other. The ones that are significantly different are 1 and 4. So those are the only ones that are not underlined with both lines. And that is the summary of the TK procedure. So should the mean MPV be used as a predictor of heart attacks? Well, based on this data, we do have evidence that the MPV is not the same for non-cardiac chest pain group and the heart attack group. But since the difference is small compared to the variability amongst each groups, it would still be difficult to distinguish between the two groups based on an individual MPV value. Even though we rejected the null hypothesis and found that those means were different, we don't have evidence that the mean is different for heart attack group and the two angina groups. So we wouldn't be able to tell the difference between the heart attack group and the angina groups. So it's not significant. If it was significantly different from all of them, then we could use it. But in this case, it's only significantly different from that first one. So it's probably not the most useful predictor of heart attack. So that is a summary of our Anova procedure for analyzing more than 2 populations.